Imagine a machine so massive that it can be seen from space. Picture it, floating above the deepest parts of the ocean, holding position against waves that would crush most structures, fighting currents that never stop pulling, resisting winds that constantly try to push it away. This machine doesn't move. It never goes anywhere, and yet it consumes more fuel than most vehicles. Every single day, a deep-sea oil drilling rig burns through thousands of liters of fuel. Enough to power an entire small town. But here's the thing. Not a single drop of that fuel propels the rig forward. Not one drop creates motion. All of it simply keeps this giant steel beast from being swept away by the ocean. The engines roar around the clock. The fuel pumps never stop. And the money, HEMORRHAGES, in real time. This is the dark secret of deep-sea energy extraction. While people talk about massive ships and jet aircraft that guzzle fuel, they overlook something far more wasteful, hiding in plain sight on the world's oceans. A deep-sea drilling platform is not just an engineering marvel. It's one of the most fuel-intensive machines ever built, and unlike a plane that eventually lands, or a ship that reaches port, a drilling rig operates in a state of permanent consumption. What makes it truly devastating is the reason for all this waste. Every system must run continuously. Every backup must be ready. Every safety measure must stay online. Because out there in the darkness, thousands of meters below the surface, the margin for error is 0-1. System fails, and catastrophe follows. So the rig burns and burns, even when it's not drilling. Even when it's waiting. Even when it's just trying to survive. This is the story of how humanity's hunger for energy, hidden beneath the ocean floor, has created one of the most wasteful machines in existence. Deep-sea drilling platforms are not simple structures tethered to the ocean floor. They are floating fortresses that must maintain their position through constant battle against the ocean itself. Thousands of meters down, where sunlight never reaches, pressure is immense and forces are unforgiving. The platform must hold its ground with precision, or everything falls apart. To accomplish this task, every system on the rig must run continuously. The dynamic positioning system uses dozens of powerful thrusters positioned around the hull, constantly adjusting to counteract wind, waves, and ocean currents. GPS systems feed real-time data. Sensors measure drift in centimeters. Computers calculate the exact force needed in every direction. This calculation never stops. It updates hundreds of times per second. Every tiny change in weather demands a recalibration of thrust, which means a spike in fuel consumption. These thrusters operate 24 hours a day, 0.365 days a year. They burn fuel not to create movement, but to prevent it. During storms, consumption skyrockets. The rig must increase power dramatically, just to remain stationary, turning off. These systems is not an option. Without them, the platform would drift. Drilling operations would become catastrophically unsafe, and the entire enterprise would collapse. At the core of every drilling rig lies a massive electrical system. One that makes anything on land look primitive. Multiple diesel generators, running in parallel, provide constant power, designed with extreme redundancy. If one fails, the backup instantly takes over. Power cables route electricity to every corner of the platform, feeding hydraulic systems, pumps, drilling equipment, and safety systems. The electrical demand is staggering and never decreases. The system must maintain perfect stability, even as loads fluctuate wildly. When drilling, operations change when weather shifts, when equipment starts up or shuts down. The electrical grid must absorb every shock without a single voltage drop. Achieving this impossible balance, the only solution is oversizing. Running multiple systems in parallel, keeping backup equipment in standby mode, and accepting that much of the power generated is simply wasted on redundancy. This redundancy saves lives. It prevents catastrophes. It also demands continuous fuel combustion, even during periods of inactivity. Every kilowatt generated must come from those diesel engines burning fuel. The system must prioritize stability over efficiency, safety over savings. The economic consequence is severe. The rig simply cannot afford to cut power, no matter how expensive fuel becomes. The true beast-consuming fuel sits at the center of the platform. The drilling system. The drill bit must bore through thousands of meters of rock, encountering layers of varying hardness. Some sections require immense torque. Rock-hard formations demand maximum power, causing electrical consumption to spike dramatically. Simultaneously, circulation systems pump drilling mud at extreme pressure. This mud serves multiple purposes: cooling the bit, carrying rock fragments back to the surface, stabilizing the wellbore. This pumping never stops while drilling occurs. Maintain pressure, or the entire operation becomes dangerously unstable. Stop the circulation, and you risk well collapse, equipment damage, and potentially uncontrolled release of hydrocarbons. The drilling and circulation systems together represent the largest single consumer of power. On the rig. During active drilling operations, they demand enormous electrical loads continuously. For weeks or months at a time, each meter drilled deeper means more power required to overcome the resistance. In deep wells, drilling can continue for months, creating a cumulative fuel consumption that reaches into the millions of dollars. Beyond drilling and positioning, the rig maintains DOT, an intricate safety system that never powers down. Gas detection sensors continuously scan for dangerous hydrocarbons. Fire suppression systems remain pressurized and ready. Emergency generators stand prepared to activate instantly. If primary power fails, emergency lighting, life support systems, communication equipment, all must remain online at all times. This constant vigilance requires constant power. Even when the rig isn't drilling, these systems continue their endless cycle. They must be ready to respond in seconds if something goes wrong. The cost is paid in continuous fuel consumption. Fuel burned to prevent disasters that hopefully never occur. It is, in essence, paying an energy insurance premium every single day. The regulatory standards that govern DOT offshore operations demand this level of redundancy and readiness. There is no room for cost-cutting when safety is the issue. Therefore, the rig burns fuel in the name of caution, in the name of preventing the worst possible outcomes. A drilling rig cannot sustain itself. Supply vessels must travel hundreds of kilometers to deliver fuel, fresh water, food, and personnel replacements. These resupply missions occur regularly, adding to the overall operational cost. During storms, vessels cannot approach the platform, forcing the rig to burn through fuel reserves, accumulating fuel on deck to extend survival time. This added weight increases the rig's fuel consumption even more. A vicious cycle of need. The rig operates with a complete workforce, sometimes hundreds of people, all requiring food, water, and shelter. This human element adds another layer of continuous consumption. The rig cannot simply shut down to save fuel when people depend on it for their survival. When all systems run continuously, fuel becomes the dominant operational cost. A single deep-sea well can consume millions of dollars worth of fuel each month. This staggering expanse must be justified by the reserves the well will produce. If geological predictions prove wrong, if the reservoir is smaller than expected, if drilling encounters unexpected complications, the entire project can become economically unviable. Before drilling even begins, companies run endless calculations. Will the oil recovered justify the fuel consumed? Can the well produce enough to cover both drilling costs and months or years of operational expense? It is a high-stakes gamble where the fuel consumption rate represents the ticking clock of financial viability. Unlike aircraft or massive container ships that command attention through speed and drama, the drilling rig's fuel consumption is quiet and relentless. There is no visible acceleration, no impressive speed to marvel at, nothing that captures public attention. The rig simply exists, burning fuel hour after hour, day after day, month after month. In terms of instantaneous power consumption, A, drilling rig might not exceed some other industrial machines. But calculate fuel consumption across months and years of continuous operation, and the numbers become staggering. A typical platform can burn 100,000 barrels of fuel in a single year, all of it consumed just to maintain position, run safety systems, and keep the operation viable. This makes Deep-C drilling rigs among the most fuel-intensive machines ever built, despite their lack of dramatic speed or impressive movement. Their power lies in endurance. Their waste lies in constancy. The fundamental paradox of deep-sea drilling is this: we must burn enormous amounts of fuel simply to access fuel that lies beneath an impossible environment. The deeper we venture, the more power we need. The farther from shore, the greater the cost. Only the largest reservoirs justify this extreme expense, which is why exploration pushes relentlessly into deeper, more hostile waters, where operational costs become almost unimaginable. The future of deep-sea drilling depends on whether the industry can develop technologies that reduce this fuel consumption without compromising safety or operational reliability. Currently, such breakthroughs remain elusive. Every system on the rig has been optimized within the constraints of safety requirements, and there is little room for improvement. Yet, the demand for the energy locked beneath the ocean remains constant. Humanity continues to require the fuel these platforms produce, which means we must accept, at least for now, that some of the most fuel-wasteful machines on the planet must continue burning fuel to provide the energy that powers modern civilization. This is the hidden cost of energy security in the 21st century, a fortress of steel. In the abyss, forever burning fuel, forever fighting the ocean, forever consuming in service of human necessity.